Solve the graph of the function f of x, I'll call f of x is equal to x plus 1 when x less than or equal to negative 1, and sine of x when x is greater than negative 1. And what I want to do is trying to get at the idea of what are called one-sided limits. And in order to define a limit, what needs to be true is that if the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x, then you can conclude that the limit of f of x as x approaches c is equal to I don't know what to say, I guess I'll say L and then right there. Then you will say the limit of f of x as x approaches c is equal to L, which is equal to R. So what does it actually mean? What does it mean for limit to approach c from the left? Well, looking at this graph over here, let's say I want to find, again, I'll call this, I'm going to do that. We can call this over here f of x. And I want to find the limit of f of x, or approximate, because again, we only have a graph here, so we can only estimate so far. The limit of f of x as x approaches 2 pi is, now I'll put approximately equal to. So, what you have to figure out first is, well, let's look at that. First you have to figure out what is the limit, I put that too far up, the limit of f of x as x approaches c from the left, approximately equal to. Well, 2 pi seems to be about, well, what, 6.28, so we're around somewhere over here, somewhere around near this region. So, as x gets closer and closer to what it looks like to be approximately 2 pi or 6.28, it seems like from the left side here, your f of x values keep getting closer and closer and closer to 0. So we would approximate the left-sided limit to be equal to 0. Now, for the second condition, we have to figure out the limit of f of x as x approaches c from the right, which is approximately equal to what? Well, again, same idea, but now we're looking for the values greater than 2 pi. So again, this looks like 2 pi, so I'm going to try to I'm going to estimate the values that are getting closer and closer to this point. So, for values greater than 2 pi, if I keep getting closer and closer and closer to 2 pi, it seems like my f of x values are getting closer and closer and closer to 0. So, from the right, I will estimate the limit is approximately equal to 0. So, finally, the limit of f of x as it approaches 2 pi, actually, I keep writing c. We actually have a c, 2 pi. So 2 pi from the left, 2 pi from the right. So we have, what is the limit of f of x as it approaches 2 pi approximately equal to? Well, a left-handed limit, we approximate it to be 0. The right-handed limit, we approximate it to be the same as the left-sided limit, which is 0. So we would estimate that this limit of f of x as x approaches 2 pi is approximately equal to 0. And again, we can't 100% confirm that. We would need to do a little bit more rigorous work than just eyeballing a graph, but that's what we would approximate the limit of f of x as x approaches 2 pi. Alright, now let's actually start working just with side limits. So let's say we want to figure out the limit of f of x as x approaches negative 1 from the left. What is that approximately equal to? So we're not concerned with the limit of f of x as x approaches negative 1. We're not concerned with that limit, we're concerned with the left-sided limits. So we would just looking at this function here. This looks to be around negative 1. So if we look at values from the left direction, or values that are approximating negative 1 or approaching negative 1 from the left, you would keep getting closer and closer and closer to. It seems like our f of x values are getting closer and closer and closer to f of x equal to 0. So we would say the limit of f of x as x approaches negative 1 from the left is equal to negative, or not negative 1, 0. Now, what is the limit of f of x as x approaches -1 from the right equal to? So yeah, now we have to keep decrementing our f of x values or our x values until we keep getting arbitrarily close to -1. So if we keep getting decreasing x values more and more and more, we're getting closer and closer to this value over here, which if I had to take a guess would be negative pi halves, because this will be about pi, so maybe this will be about somewhere about pi halves. So again, but the only way we would actually be able to really show that rigorously is through a little bit more work. So I would approximate this to be negative pi halves, especially since the sinusoidal function we're probably dealing with pi. So something interesting here, that the limit from the left and from the right of -1 are approaching different values. Interesting. Alright. So now this is okay, so we're done with that. Now something I want to take a look at is this guy over here. The 10 over x minus 1. And what I want to figure out is if I was given this graph, what would be the limit, and now I'll call this g of x, I'll do my own in the same color. The limit of g of x as x approaches 1 approximately equal to. So graphically, we're dealing with the problem. Because when you're looking at this graph, we can't really approach it because if we're going from the right side, we'll kind of just stop there. We kind of just stop at 3, we can't really get anything from there. And if we go from the left side, we're also not really able to see what's going on around x equal to 1. So really, when we're trying to work with graphs, we want to see how it behaves around x, whatever value we're approaching. But in this case, we can't really do that because our scale is pretty terrible for estimating this limit. So thankfully, we can just zoom out of this. We can do that, and we can try to actually get a better look at how what this limit is approximately equal to. But if we were just given this graph, we wouldn't really be able to, because again, graphically, limits are pretty much all about looking at the behavior of your function around the x value you're approaching. But with this graph, because we can't really do that, the scale is pretty terrible, then we can't really make any estimations of this based of just the graph. Alright, now I'm going to look at these four, and these four are interesting functions in terms of their limits. So, first one, first I want to know what is the limit of, now I'll call this h of x, as x approaches 0. So what would that be equal to? So again, you can first find the limit of h of x as x approaches 0 from the left. And that really just means looking at values that are less than 0 and seeing what they're approaching. So from the left, you see that we're getting more and more up, but again, we're having a little bit of issue with scale. So why don't we scroll up and see what's happening? Let's keep going until our function actually intersects x equal to 0. So we've been scrolling for a while and we've not reached 0. So that probably tells us that we have an asymptote. And really you can just figure that out because we're defining by 0 over here. So you probably expect that x equals 0, you're gonna be experiencing some weird stuff. And that weird stuff, it seems to be that actually I could just don't press this button here. So the weird stuff, oh wow, okay, it wasn't even censored. So the weird stuff that's going on is that we do have what seems to be, at least just graphically, is that of a vertical asymptote. So you would say that the limit of h of x is which is from the left. Well, it's never going to cross 0, or I guess I should say never going to cross 0, but it doesn't really have any behavior x is equal to 0, because it seems like as you keep getting closer and closer to 0, your h of x will just keep increasing, increasing, increasing. So you would say that the limit of h of x as x approaches 0 from the left does not exist. And specifically, you would say that the limit goes unbounded, or that the function goes unbounded. Either way works. I think I usually write function goes unbounded. Function goes unbounded at x is equal to 0, or at least from the left. But you can look at it from the graph for values approaching 0 from the right, and it looks like we're having the same story. So you could just say x is equal to 0, just like that. Now, a notation you'll typically see when it comes to unbounded limits is that you would see people write the limit of h of x as x approaches 0, and now we can just generalize it because from the right we already figured out that graphically it looks like it's going unbounded. So you would say at the limit of h of x as x approaches 0, you see people sometimes write infinity. So it does get at the idea of, yes, as you keep getting closer and closer to 0, your h of x values keep getting closer and closer and closer to infinity, or that the h of x values keep increasing. But this kind of notation is kind of incorrect, and I'm not gonna go because it does kind of the more rigorous definition of the limit. This kind of falls this definition or this notation saying the limit is equal to 0 starts falling apart. So this notation definitely is typically considered incorrect. Although you will see people write it, and it is a notation you would see on the AP exam. However, the correct notation would really just be to say that the limit of h of x as x approaches 0 does not exist, or you would say that h of x goes unbounded at x is equal to 0. So this is one of those types of non-existent limits, and I don't want to I can't keep a list of it because I can't keep the tool for too long because then it starts lagging for some reason. So I have to keep deleting it. So uh, non-existent limits. So we have unbounded limits. Now, let's look on these other functions. Let's look at the absolute value of x over x. So here we have this, and what is going on with this graph? Well, let's try to estimate the limit of j of x. I don't want to use I of x. The limit of j of x as x approaches 0 is approximately equal to what? Well, again, first you have to figure out the left side of the limit is approximately equal to 1. So from the graph, it looks like it's constantly at j is equal to 1, so I'll say that it is approximately equal to 1. So what about the limit of j of x as x approaches 0 from the right? Approximately equal to. So again, here, it seems like it's also constant, but this one looks like it's has a constant value of j of x is equal to 1. So s of it's supposed to be negative 1. So I'll estimate this to be approximately equal to 1. So what will we say the limit of j of x as x approaches 0 is? Well, we're having a problem here because the only one limit is defined is if the left side of the limit and the right side of the limit are equal to each other. However, of course, negative 1 is not equal to 1. So when the left and the right side of the limits are not equal to each other, then this will be another example of a limit that does not exist. And there's not really any notation for one side limits not being the same. You would just say that it doesn't exist. So you would say another type of non-existent limit is unequal one-sided limit. Alright, now we want to the next one, which the next one is, I think, my favorite one of these to look at, and I think you'll see why immediately. So, we have the graph of the function sine of 1 over x, and we want to estimate the limit of k of x as x approaches 0. What is that approximately equal to? So again, our first question, what is the limit of k of x as x approaches 0 from the left approximately equal to? Well, what does it look like it's approaching? You can getting closer and closer to 0, and we kind of just going all over the place. So again, this is another probably one of those issues with scale. So why don't we try to zoom in and see what it's really approaching? Because this just seems like a block. Maybe we zoomed out too much. Actually, I want to look at this because it's getting messy. So we're still seeing this block of purple, and so we just have a block of purple. So the limit doesn't actually seem to be approaching anything because, well, what is approaching? It keeps going up and down, 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 but it doesn't seem to be going to one specific value. It just seems it's like it's always going between, which is amount more. It seems like it's always going between -1 and 1, but it doesn't actually converge to a specific value. It doesn't go to one specific value. So this is a pretty rare example of a non-existent limit. So you would say that the limit does not exist, and that's because the function is experiencing an oscillation. I guess you could say an infinite oscillation because, well, it's oscillating around the value. It's always oscillating between -1 and 1. Anywhere in the neighborhood of x is equal to 0. So you can't really determine it. So you can't really determine it. So you would say the limit doesn't exist. And this is a very unintuitive limit because the range, well, x is equal to 0 is a finite value. The range is a finite value. It's a finite set, -1, 1. But somehow the limit doesn't exist because the one way you can think about it is that as x approaches 0, the period of the function is approaching 0 as well. So it is pretty unintuitive, but something very cool to see, especially when you keep zooming in more and more, because it does kind of seem very interesting. X equal to 0 finite, and its range, or it's also what it's oscillating around -1, 1, a finite set of values, but the limit doesn't exist. So, alright, so that's another example, and the last one I have over here is 1 over x. So, I want to figure out the limit of L of x as x approaches 0 approximately equal to. Again, the first question, what is the limit of L of x as x approaches 0 from the left? So, from the left side, it looks like it's approaching. It seems like it's going unbounded, but this one is going unbounded in the negative direction. So it does go unbounded, and yeah, see, this is what happens when I have the pen to open for too long, it starts lagging. So unbounded in the negative direction. So like that. So already, just for the fact that a one-sided limit is unbounded, we can immediately determine that the limit of L of x as x approaches 0 does not exist. And something interesting about this is that it's not just that it's unbounded, but if you were to look at the right-sided limit, it looks like it's going unbounded in the positive direction. So it's not only that it's going unbounded, but it's actually that the one-sided limits are unequal. This one's going unbounded in the negative direction. This one's going unbounded in the positive direction. But either way, you would say that because the limit goes unbounded at x is equal to 0, you would already, or you immediately just from that say that the limit does not exist. So this is kind of a combination of being unbounded and having unequal side limits.